time, let me just remind you that we are thinking about now just the narrow bands in the twisted bilayer graphene. We have renormalized down to just this Hilbert space. And we argue that, well, the bands are still narrow and the Coulomb interaction is going to dominate let's see, the Coulomb interaction is going to dominate the kinetic energy, the renormalized kinetic energy. There are certain statements we can make about this, namely, at the charge neutrality point, any many-body state that's annihilated by this fluctuation density operator delta rho is going to be a ground state because the repulsive interaction is positive semi-definite. And so if we can zero something out, it's got to be a ground state. It's a little bit trickier at even integer filling away from the neutrality point. But nevertheless, there are certain statements one can make about this. Namely, if you can find an eigenstate, many-body eigenstate of delta rho, which is not actually that difficult at even integer filling, you just simply fill, for example, a particular valley with a particular spin. Such a state is going to be an eigenstate of this, and its energy is actually pretty decent. It turns out to be a ground state. You can check this numerically. There's also a deformation of this Hamiltonian into so-called flat metric condition in which this can actually be shown to be the ground state. And as you move away this deformation, you can check numerically that it remains a ground state. And this was done in this very nice series of papers by Andre's group. But this flat metric condition was sort of discovered in real space in this first paper in this list. Now, at odd integer filling, it's harder to make exact statements unless we have both the flat metric condition and also if the sublattice is perfectly polarized, such that we are in the chiral limit. In this case, the Chern states will be the ground states. And again, you can try to deform from this and ask, how far does this survive? This was also done numerically in this very nice series of papers. And it survives up to a certain ratio of W0 to W1 without the flat metric condition. But then, as I will show you, it will actually go away when W0 over W1 is close to 0.8, which is believed to be the realistic value. So that there we will get actually a larger degeneracy of states. But in any case, one way or another, we see that these generalized ferromagnets are favored by the projected Coulomb interaction. In real space, this was first shown in this 2019 paper. And there was an explanation for this, namely, you show how the famous super exchange that we know in the Hubbard model is defeated because of the longer range nature of the Wannier states and the projected Coulomb interaction. In fact, it favors direct ferromagnetic exchange among the sites. But you can also study this in different bases, and in particular, you can go to momentum space, so Bloch bases, or you can go to hybrid Wannier bases, or you can go to 2D exponential localized bases, as we will discuss today. Okay, so now, so it's very simple to construct. So let's think for a moment, just pedagogically, that we are back at the charge neutrality point. So that all we have to do is find a state that is annihilated by this delta rho. That's not difficult to do. For example, a valley polarized state will do. If you put at charge neutrality point all the electrons, let's say, into valley k prime and leave valley k empty, delta rho will annihilate such a state. But this is not the only state. Because which is the ground state at the charge neutrality point for this Hamiltonian, and that's because there is a larger global symmetry in this strong coupling limit, namely the spin value U4 symmetry. And the way to understand this is as follows. The particle hole symmetry I mentioned yesterday allows us to relate a state in the narrow bands whose kinetic energy would be sketched over here. So there'll be some E and K. So N is the band label. And if you give me such a state within the narrow band, within a particular valley, then I can immediately generate a state which is at kind of a reflected K point relative to this, with the negative of that energy. And I can do that by complex conjugation, flipping the sublattice. So sigma x acts in the sublattice, and at the same time acting with I mu y. So mu y is the y Pauli matrix acting in the layer space. Okay, so this operation is going to take you between these two branches of the narrow band spectrum. Okay, and it turns out, so sigma x here acts on sublattice, and so it turns out that now if you take the projected density operator, which is now explicitly over here, it will have the following form. So the upper two components live in a valley K. Okay, they are labeled by their band index, which is plus for the upper branch, minus for the lower branch. Since this is at a position R, we're going to be in general mixing K and K prime over here, and the product of the wave functions is going to be sitting in these A, B, C, D coefficients. Now, it turns out that because of this particle Hall symmetry, we can relate the coefficients in the valley K to the coefficients in the valley K prime, such as this. And this shows you that this 4x4 matrix in the valley and band space, you see the spin is sort of just riding along, clearly commutes with these four other 4x4 matrices. So let me just walk you through this. So the first one is trivial, it's just an identity. The second one is tau z, tau acts in the valley space, and the identity acts in the band space. Okay, so clearly this is fine because we don't have any coupling between the two valleys in the density operator. So there's no this should be obvious why the second 4x4 matrix commutes with this larger 4x4 matrix. And what this just corresponds to is simply independent spin rotations within each valley. Okay, but if this is all that there is to it, then the symmetry would only be U2 cross U2, which is actually the symmetry of the Bisset and McDonald model. However, the projected Coulomb interactions have a larger symmetry, and that's because there is another pair of 4x4 Pauli matrices, again, tau acting in the valley, sigma tilde acting in the band in this particular case, which also commute with this 4x4 matrix. And now, because we are changing the valleys, we are able to rotate continuously between them. Okay, so these will be the generators. And so this actually is even larger in the chiral limit, because there's a basis in which the coefficients B and C will go to 0, and then the whole thing is just diagonal. And in that case, the symmetry is not only U4, it's actually U4 cross U4. So in every Chern basis, you can perform these rotations independently. And so what this means is that if you find a ground state for the projected interaction Hamiltonian at the charge neutrality point, let's say, then I can generate a manifold of states, depending on whether you're in a chiral limit or not. If you're not in a chiral limit, I can generate a manifold of states by a global spin valley U4 rotations. And this is interesting because some of these states contain, for example, equal superposition between having an electron in valley K and valley K prime. And these are so-called intervalley coherent states. Now, if you're in a chiral limit, you can actually perform other rotations, which will, for example, take this valley polarized state and turn it into, well, you can show that it is degenerate with, for example, a Chern state. Okay. So even though it is a generalized ferromagnet, it's not necessarily just a spin ferromagnet. There are other states within this manifold. Okay. So that's the new result on the strong coupling limit. We should be thinking about this as this generalized ferromagnet. And as you see, it's very different from what would happen in a Hubbard model. In an ordinary Hubbard model, the degeneracy would be much larger. In a strong coupling limit, without introducing any hopping, then let's say you are at half filling of a square lattice Hubbard model. You have one electron per site with a spin that can point up and down. But that spin is independent on each site. So your degeneracy would be exponential, 2 to the power of number of sites. In this case, the degeneracy is nowhere near that large. The degeneracy is really just global rotations, so it's polynomial in the number of sites. And the reason for the degeneracy being much smaller compared to the usual Hubbard model is actually the extended nature of the, let's say, 2D localized Wannier states. You can see this in momentum space as well, but I think it's clear in the exponentially localized basis. If you were to project the interaction onto this, you wouldn't get just the Hubbard model. You would get intersite exchanges, you would get assisted hopping terms, you would get pair hopping terms. And so they sort of propagate the information, they link various sites in a way that the ordinary Hubbard model does not, already at the level of the interaction, before you ever brought back any kinetic energy. So that's the reason for lifting of this massive degeneracy that you would naively have gotten in the ordinary Hubbard model. Okay, so as I mentioned, one example of such a state would be a valley polarized state. It's a ground state, but in fact, any state that can be obtained from valley polarized state by spin valley U4 rotation is also a ground state. Now, let's stick with the charge neutrality point. We'll discuss the other integer fillings later. It turns out that we can also build exact excitation spectra on top of these ground states. So why is that? So usually, this is a difficult numerical problem. It's a many-body problem, but in this particular case, there's a simplification. And the key observation, which was actually made independently by us and by Andrei's group, is that because the state upon which this fluctuation density operator acts is annihilated by it at the charge neutrality point, when I take delta rho, and I act on a state, which was the ground state, but then I have some operator x acting on that state. So let's say that x will try to create an excitation on top of our ground state. And naively, it looks like a complicated problem. It's a v delta rho. But the simplification comes from the fact that when you bring the delta rho all the way to the right, then omega gets annihilated by it. And therefore, you can rewrite every product of delta rho x as a commutator of delta rho x. So that's the first term. And of course, you can continue doing this. Now you would have a delta rho times a commutator. But again, because delta rho annihilates omega, you can write it as a commutator. Now, what does this buy you? Well, what it buys you is the fact that now imagine for a second that x is just a creation or annihilation operator. So you're trying to create single particle excitation. So let's count. Delta rho is going to contain one creation operator and one annihilation operator. Let's say x is a creation operator. Well, this commutator is going to return another creation operator. It's not going to return two creation operators and one annihilation operator. It's just going to return one creation operator. Okay. And then if you make another commutator, with another creation annihilation, with a creation operator, again, you only have one creation operator left. You won't get this additional particle Hall excitations, which usually would happen. And so that means that on the right-hand side of the equation, you are left with some convolution in real space of just a single creation operator. But that means that you can solve an eigenproblem, because you would have an energy times creation operator acting on the ground state. So on the left-hand side, you just have a creation operator. On the right-hand side, you have some convolution of a creation operator. And so you're dealing with a one-body problem. Okay, so now we just have to diagonalize a simple matrix. In fact, because this is a translation symmetry, you can take advantage of that. And all you have to diagonalize really is just a small matrix, in fact, just 2 by 2 matrix within for each K point. And then you get exact excitation spectra on top of this. Okay, so there's no approximation here. All the approximations were already stated, namely, we're going to ignore the kinetic energy and start by building the many-body spectra of the projected Coulomb interactions. And so you can go from the top equation to the bottom equation simply by matching the operator content on the left and the operator content on the right. Now, to understand the degeneracy, you also need a little bit more. You need to know whether your creation operator is, for example, trying to add into a field state, in which case it's really annihilating it itself. But then you have to do kind of a posteriori. But in any case, let's say you went through this procedure and you did this. So these delta rho operators, they contain the wave functions that we have left after the projection, after the RG, and there's going to be some convolution of 4 of these wave functions. Okay. Okay. Let's say we now match left and right and solve the eigenvalue problem. What we find is the following: the charge neutrality point for the results of the RG that I showed you before for the wave functions, we find that adding a single particle or single Hall to the problem is gapped. So all the states that I showed you that belong to this U4 manifold are gapped. So they're insulating states. That's not so surprising because we solved the strong coupling problem. But, and of course, and the size of the gap is set by the Coulomb scale, which is set by the dielectric constant of the environment, and the Moret period, Lm. But the surprising or the more interesting part is that even in strong coupling, so I have not brought back any kinetic energy at this point, the excitations disperse. In other words, and the dispersion, if you look here, is actually comparable to the gap itself. Now, so in other words, what this means is that this is very, very different from what would happen in a Hubbard model in strong coupling limit. In a Hubbard model in strong coupling, when you are, let's say, at the half filling, you can try to add a particle to a fully filled lattice. That's going to cost you a Hubbard U. Okay, good. That's a gap state. That's similar to this. But that particle would just sit there. If you want to move that particle around, you have to bring back the kinetic energy, which comes in perturbatively. And through second order processes, in principle, you could move at excitation. However, as you see here, without ever bringing in kinetic energy as a perturbation, our excitation moves. And in fact, its dispersion is itself set by the Coulomb interaction. Now, that's a new aspect of this problem. How is this happening? Well, it's happening because the projected Coulomb interaction, again, contains terms which describe, for example, assisted hopping, or they describe pair hopping. And these terms are able to delocalize your excitation even in strong coupling. And that, as we showed in this 2019 paper with Jian, is actually a direct consequence of the non-trivial topology of the narrow bands. So the fact that the Wannier states in 2D localized Wannier states have this extended nature. I will discuss that as we go along. So this is the first kind of an interesting thing. So now, of course, you can start asking, well, what would happen if I start adding excitations to this strong coupling problem? Well, presumably they would want to go into the vicinity of gamma point, and we will discuss this as we go along. Now, notice that this dispersion is extremely different. It's very different from the dispersion you would have gotten from the Bissett and McDonald model. In the Bissett and McDonald model, you have two narrow bands, and these two narrow bands touch at K and K prime points in the Moret-Brillouin zone. Here, the dispersion is gapped. These two bands touch at gamma. Okay, they touch at M, and they also touch at K and K prime. But the shape of this is very, very different. The minima are at gamma. They're definitely not going to K or K prime points. Okay. So we can build other excitation using this technique. Nobody tells me that I should choose this operator X to be creation or annihilation operator. I can, but I can choose this X to be particle Hall operator, so D dagger D type operator. And again, the same logic goes through. Delta rho annihilates on the right, so I can continue thinking about this as a commutator, and this just becomes a nested commutator. The operator content on the right does not change. If I'm going to have a D dagger D on the left, I'm going to get some convolved, but still just D dagger D on the right. I won't pick up any other operators. And so again, I can close this system of equations and just diagonalize. I mean, in this case, it's a little bit more complicated. It's a larger matrix to diagonalize, but you can still do this on your laptop. And so in this particular case, I'm going to show you the spectra we obtained for the neutral collective excitations at the charge neutrality. So again, it's a spectra of a D dagger D operator added to these exact charge neutrality point ground state. So first, notice that the red line here is the onset of the particle Hall continuum that you can obtain simply by thinking about the kinematics of single particle excitation, just from this blue curve. Okay, so everything above this red line is part of a continuum. Below this continuum, we see bound states, particle Hall bound states. And in particular, we see a set of branches at energies which are significantly removed from the rest of the states, which form our low-lying collective modes. Now, what are these modes? So we see that there is a quadratically vanishing collective mode at the gamma point. That's a ferromagnetic ghost zone. Okay, you know that ferromagnets have Heisenberg ferromagnets would have a quadratically dispersing ghost zone mode. So we see this explicitly in this calculation. But then in addition to that, we see that there is another mode which softens. Now, that softening has to do with our flowing closer to the chiral limit. Because in the chiral limit, the U4 symmetry that I discussed enlarges to U4 cross U4. And so softening of this mode is a signature of the proximity to the chiral limit. This is the so-called pseudo ghost zone mode. And then in addition to, so the gap here is about 0.2 in the Coulomb units. So this tells you a little bit about how much of an anisotropy you have for different Chern sectors. Okay, and then finally, there's this rather interesting low-lying branch, which does not become gapless in the chiral limit, but nevertheless, it's still rather soft compared to the rest. And I don't know if you can see this, but there are actually two branches which cross here. So there's actually a symmetry enforced crossing of these collective modes at the gamma point. And they transform under a non-trivial representation for the threefold rotation. So these are actually the nematic collective modes in the system. Okay. Now, what can we use this for, apart from what I just mentioned as a physical interpretation? Well, imagine we sit at the gamma point. Well, that means that we have the exact wave functions and the exact energies of any charge neutral operator of the form d dagger d, whose total momentum is 0. That means we can take the kinetic energy operator, whose momentum is also 0, and decompose it as a linear combination of the operators we have at the gamma point. And that means we can do an exact super exchange calculation. We can now go to second order imperturbation theory, act on our ground states with the kinetic energy operator. We know how to decompose it into the exact eigenstates, eigenoperators of the Hamiltonian and the gamma. And instead of just putting a bound on the super exchange, so the effect of the kinetic energy, we can just compute this exactly. Okay. And this was done in here as a function of the twist angle. So the blue line here shows the charge gap, and the red curve shows this super exchange. So super exchange is in quotes because this is sort of the manifold is ferromagnetic of this generalized kind, but then the kinetic energy, which itself does not have a full U4 symmetry, only U2 cross U2, is going to try to introduce some anisotropies here. Okay. Now this anisotropy has been argued to be good for superconductivity by proponents of the skyrmion-mediated superconductivity. But as you see, so in other words, in that theory, as J goes up, TC would go up. But as you see, this J is actually minimum at the magic angle, while I showed you previously data from experiments which showed that the TC has a maximum at the magic angle. So in any case, the point I'm trying to make here, additional point I'm trying to make here, is that we can find out how large is this super exchange. Okay, so for example, in a Hubbard model, the way you would do that, again, is you would bring back the hopping. You would treat the hopping in second order perturbation theory, and then you would ask, is this J that you generate large or small? If it's too large compared to the charge gap, well, then you may want to start suspecting that your strong coupling limit is not that well justified. But as you see here at the magic angle, the super exchange is very small. So in Coulomb units, its minimum takes this value. And so in fact, this is the justification for taking the strong coupling limit in the last step. Okay, whatever kinetic energy is left, it's just a perturbation trying to split this U4 or even U4 cross U4 manifold. Okay. Now, I would like to go back to this spectrum and try to understand why it has the shape it has. Why does it have a minimum at gamma, for example? And how will it depend on the screening due to the metallic gates of the Coulomb interaction? So for example, if I imagine a system which has one gate above and one gate below, symmetrically placed around the twisted bilayer graphene, and I could imagine that I can change this distance, then the long-range part of the Coulomb interaction will be screened more if I bring the gates closer. I'd like to understand what happens to this spectrum. Okay, so to do that, let me go back through the derivation and actually generalize this so that we are not just at the charge neutrality point, but we can be at any integer filling. But I'm gonna simplify our life a little bit and go to the chiral limit. If we understand it in the chiral limit, we can do the numerics away from the chiral limit, and we'll see that while there are some changes, they are not going to change the fact that we can actually understand where these changes come from. So again, it's basically the same idea, except for now, since we are at integer filling, delta rho no longer annihilates our ground state, but it turns out that when delta rho acts on our states, as I mentioned, the ground states turn out to be eigenstates of delta rho. And so in this case, you just replace the result of the action of this operator onto the ground state with a C number function that is written over here. And again, that does not change, which can be written in terms of the exact narrow band wave functions. And so again, it doesn't change the operator count. The number of operators on the left of this equation and on the right of this equation are the same. And so you don't really have to solve a hard many-body problem. You're only just solving a few-body problem. So if you go through this, you notice an interesting thing. Namely, let's consider just single particle excitation. So we would substitute either the annihilation operator for X or the creation operator for the X. Now, the first equation, the first term on the right-hand side of this equation does not care whether you have a creation or an annihilation operator because you do the commutator twice. But this term, which is present only if you are away from the charge neutrality, actually does care. Because think about this delta rho, it's something like d dagger d. Now, if this X is d, then you're going to get plus d dagger as a result of this commutator. On the other hand, if this X is, so first of all, it's d dagger. So if this X is now d, and you have a d dagger d commuting with d, then it's going to be minus d. So you pick up a different sign depending on whether you're adding a particle to the ground state at a non-zero integer filling, or whether you are taking a particle away. And this will be very important for us as we go along. In any case, the result of this operator matching can be written through our exact wave functions. These are block functions labeled by the band index n and the block momentum k. And these sums over the band indices are only over the narrow bands we've already projected. Okay. So we can think about the first term as being an exchange term, and we can think about the second term as being the direct or the Hartree term. But I want to stress that this is exact. This is not a Hartree-Fock approximation, which would not be justified by any other theoretical reasons. This is just an exact calculation. All right. And so in principle, I could just plug in the numerically determined wave functions and compute this numerically and just report the result, but I wouldn't necessarily understand it. So I'm trying to actually explain why the spectrum looks the way it does. Now, it turns out that in the chiral limit, you can show that this matrix in N and M at every K is diagonal. And the reason for this is a combination of two symmetries. The first one is so-called chiral particle hole symmetry, which is a symmetry that's present in the chiral limit, in addition to the C2T symmetry that has been discussed previously. So now, let me first report the result of this calculation. So if we were to take away a particle, let's say at positive integer filling, then, as I mentioned, one of these terms subtracts, so this, let's call it Hartree-like term, subtracts from the Fock term, while if we were to add a particle, then it adds. And so now all we have to do is figure out what these dispersions are independently for the exchange and for the Hartree part. Now, we're gonna allow, as I mentioned, a additional parameter in our problem, namely the distance to the two screening layers. So in other words, physically what we are thinking about is that our twisted bilayer graphene, which is sandwiched in the hexagonal boron nitride layers, has a metallic gate above and below, and let's just say it's symmetrically above and below, and the distance that the metallic gate has above our twisted bilayer is denoted by this Greek letter xi. And so then just from your elementary electrostatics course, you know that there would be a series of image charges that occur for any test charge in the twisted bilayer graphene due to these metallic layers. And if you just had one, you would have a dipole problem. If you just had one gate, but because you have two, now they start mirror reflecting, and you get this infinite series of charges. Now it turns out you can sum up this series. You can look at it in real space. You can look at it in momentum space. In real space, what happens is that the interaction is exponentially small, as opposed to just a dipole interaction, at distances larger than xc. At distances much shorter than xc, the interaction is still 1 over r. So in momentum space, that interaction has the following form. It's the standard Coulomb piece, which I discussed before, but now it has this additional factor of hyperbolic tangent, qc divided by 2. Okay. Okay. So I'm going to plot the dispersion contribution from the exchange term first on the left, that's shown over here, as a function of the distance of the metallic screening layers to the twisted bilayer graphene. And again, Lm is the Moret period. So what we see is that this exchange term has sort of similar shape, almost the same shape, even though we are moving the gates further and further apart from the twisted bilayer, but that the gap is actually changing. The gap grows. So that should not be super surprising that the gap is growing, because after all, we are changing the strength of the Coulomb repulsion as we are moving the gates further apart, and we're making it stronger. So indeed, the gap is growing as we are moving the gate further apart. But why is the shape not changing? And why is the minimum at gamma? That's not obvious, because the entire dispersion curve is set by the Coulomb interaction. So that's this epsilon f term in the chiral limit. Again, I just want to stress that we haven't brought back any kinetic energy here. This is all strong coupling single particle excitation. And as you see, even in the chiral limit, the single particle excitation disperses. So for now, I want you to focus on just the solid lines, which are a result of a calculation in the block basis. The dots are actually calculation performed by Wannierizing this problem, which I will discuss in just a second. And as you see, there's a perfect agreement. So you definitely can Wannierize this problem in 2D. So 2D localized. Now, the Hartree contribution, the direct term, is plotted on the right here. Again, it has a minimum at gamma. Its width is set by the Coulomb interaction. But notice it has almost no dependence on how far I put away the gates, as long as the gates are at least 1 Moret wavelength away from the twisted bilayer graphene. So 1 and above. So there's a big difference between the Hartree contribution and the exchange contribution in that dependence on xc, the distance to the gate. Okay, now if you look at the actual numbers, you notice that the bandwidth is almost the same for the curve on the right and the curve on the left. It's about half a Coulomb unit, maybe just a little bit less. Now, also the shape is almost the same. Okay, so you can see what's going to happen if we are at mu equal to 1. So because the strength of the term that we are adding or subtracting depends from the Hartree, depends on the filling, at mu equal to 1, if we add a hole to the system, then there will be a cancellation of this dispersion from the exchange part and this dispersion from the Hartree part. And in fact, our excitation will be almost completely flat. The band for the holes at mu equal to 1 will be almost completely flat. On the other hand, for the particle at mu equal to 1, the two curves will add and the bandwidth will double. So we'll see a huge asymmetry between the particle and hole. And of course, if you were to go to the mu equal to -1 filling, this will all get inverted. In other words, trying to add an excitation that would move our filling closer to the charge neutrality point is going to flatten out the spectrum at nu equal to 1 or nu equal to -1. But if the excitation is moving the filling away from the charge neutrality point, so towards the remote bands, then in fact the bandwidth grows. If we were at nu equal to 2, then in fact we have to add 2 of these or subtract 2 of these curves on the right from the left curve, and then the dispersion will invert. And again, there will be a huge asymmetry because adding a hole at nu equal to 2 will mean that the hole is going to go into these flat portions of the dispersion, while the particle is still happily going to go to the minimum at the gamma point, which is nice and deep. And in my opinion, this is the explanation for the cascade transitions, as I will try to argue. Okay, so we're going to now switch the basis. Instead of describing this in a block basis, which we certainly can, we can describe this in a churn basis as well, block churn basis, and do the calculations numerically. We're going to try to linearize this problem. Now, you can object, you can say, well, how can you linearize this problem? It's topological. Well, you need to remember, I think Titus mentions as well, really the only obstruction to 2D linearization is if you have a non-zero churn number. Now, even within each valley, as I showed you from the Wilson loops in a previous lecture, the churn numbers of the 2 bands are opposite. So we have a 1 plus and 1 minus. As Andre said, it's more like a quantum spin Hall problem than it is like a churn insulator problem. Now, that is topological, but the total churn number vanishes. What this means is that strictly, if all you're after is finding a 2D exponentially localized Wannier states, it can be done. There is no obstruction to building 2D exponentially localized Wannier states. Now, there is an obstruction to also demanding that the symmetries, which made this problem topological, are implemented in some simple on-site fashion. And that part will have to get sacrificed. By the way, it doesn't actually mean that you break symmetries, as is usually stated in the literature, that in order to be able to localize topological band without churn numbers, you have to break symmetries. Because the mapping between the Wannier basis and the block basis is unitary. There's no information that can get lost. So rather, the more correct statement is that the symmetries are not manifest, but the symmetries are still there if you do this mapping exactly. In any case, in this particular case, if we do this in a chiral limit, as was done in detail in this paper, so I encourage you to read the papers, particularly if you want to see how the symmetries are implemented and which symmetries cannot be implemented in a simple site-to-site fashion. In particular, C2T in here is not, but I think there was a question during one of the Andre's lectures, how about particle Hall symmetry? Particle Hall symmetry is implemented as an on-site symmetry in these 2D localized bases. In any case, our Wannier states are centered on the sites of a Moret honeycomb lattice, so AB or BA sites, while the peaks in the wave functions appear at the centers of these hexagons, which are the AA sites. These are the well, I guess famous because they have been discussed quite a bit, so-called fidget spinner, these 3-peak Wannier functions for the narrow bands. So what I'm showing here is just a real space picture of W dagger W for this particular site. Okay. So 1 and 2 in here just correspond to 2 different sites within the unit cell. Okay. So in this particular case, they are centered on this white dot. Now, it will be helpful for us to also know what is the real space structure of a product of 2 Wannier states, which are centered on different sites. And in this chiral limit, as we show in this paper, you can go into a basis in which this product is purely real. So we can just plot it as is. And as you see, it clearly has this sort of a dipole type structure. Now, one thing is for sure, the real space structure cannot have a monopole component. And that's because these are true Wannier states, so they are orthonormal. And so if you were to integrate this overall space, you have to get 0. Okay? And since this is real, somewhere you're going to get positive, somewhere you're going to have to get negative. So the monopole contribution to this multipole expansion has to vanish. Unlike for the on-site term, but this one, there certainly is a monopole contribution. But all the other ones, they don't have a monopole contribution. So now that we have some idea, and by the way, the further apart we put the centers of our Wannier states, the smaller are the wave functions. You see on this color bar, it's getting actually fainter, and well, the colors are saturated, but the color bar is changing its magnitude. So indeed, the further apart you put them, not surprisingly, they get smaller and smaller because they are exponentially localized. But for the nearest neighbors, for example, it's not really negligible. Okay, and even for the next neighbor, it's not really negligible. So now we would try to use this basis to rewrite our dispersion. The details are shown in this paper, but the result is here. So what I'm doing here is I'm taking this, let's see, I'm taking this Fock contribution and I write it in a type binding form. So I'm reporting here just the hoppings for the Fock contribution as a function of the distance between the two sites. And as I mentioned, this matrix is diagonal, so we are only remarkably only going to hop between the same sublattice sites. The hopping between different sublattice sites actually vanishes identically in the chiral limit. So the first equation is the expression for the hopping constants for the Fock contribution, and the second term is the expression for the hopping constant in the Hartree contribution. Now, let's start by thinking about the Hartree contribution. There's a piece which, sorry, this is a mistake. The oval should be on the right. The sum over r prime here guarantees that this term on the right, so sorry about this. This oval should be circling the second parenthesis, not the first parenthesis. This term here is periodic because of the sum over r prime. And so because it's periodic, if we think about this as an electrostatic problem, we have a periodic charge distribution. This first term, which I labeled periodic, which is not periodic, this is just a localized term, represents some charge distribution, Coulomb interacting with some periodic charge distribution. Okay, that's the electrostatics of this problem, this fictitious problem. So now you can go to Fourier space here, and you notice that because this is periodic, it's only going to pick up the momenta of our Coulomb interaction, which start at the reciprocal momenta. So it starts at q equal to 0, but at q equal to 0, this actually vanishes because of the background charge contribution. So the first term that will actually contribute here is the Morel reciprocal lattice vector. Okay, and that's because the second term in the parentheses is periodic. Okay, so the fact that this is localized doesn't matter too much. And so if you look at the value of this momentum in the units of the Morel period, it's actually about 7.25 divided by the Morel period. So if you now plug it into this formula, you see that you're evaluating the hyperbolic tangent at least 3 and some change, which is already pretty close to 1. No matter what you put for Xi, as long as Xi is larger than 1 Morel period. So what this tells you is that the reason why we found this Hartree contribution to be independent of the gate distance is because of, it's actually very simple. It's because we are only picking up the large wave vector, relatively large wave vector part of this Coulomb interaction due to the periodicity of this charge distribution. Okay, that's the reason why it's basically Xi independent, while once Xi is larger than 1 Moret period. On the other hand, if we look at the exchange contribution, it's different. In this case, both fictitious charges which contribute to this electrostatic problem are localized. Now, let's say, and so what does this mean? It means that it's going to probe in principle, the entire Q dependence of this function. In particular, it can probe Q much less than this Moret wave vector. Now, let's say that we are interested in the on-site term. Okay, so this, in our type binding parameterization, this would correspond to an overall shift of our band. So in this case, capital R would be 0. So if capital R is equal to 0, in sum over R prime, there's also a term which has an R prime equal to 0, in which case both of these binary states are centered on the same site. And since, again, we're assuming that capital R is equal to 0, so we're looking at the on-site term. In the sum over R prime, again, capital R prime is 0. And again, the term on the right is also evaluated on the same site. Okay, so we pick I in the sum over I, we pick I equal to 1. In this case, we're going to get a fidget spinner Coulomb interacting with another fidget spinner. But as I mentioned, these fidget spinners, they contain a monopole contribution. So if you go to momentum space, their momentum structure is shown in this plot A. So now you have VQ, rho minus Q, where rho Q looks like this. You see it's peaked near small wave vectors. And so it's certainly probing the interaction at small Q, because this localized charge distribution contains small wave vectors in this distribution. And so if Q is much less than 1 over Xi, well, if Q is much less than 1 over Moret lattice distance, then even for Xi larger than Moret lattice spacing, the R equal to 0 contribution to the hopping is still going to have a gate distance dependence. And that explains why in the Fock contribution, we see an overall shift of our curves. Okay, so as we change the gate distance, the gap is growing. Okay, that's the reason for it, because we have a direct Coulomb repulsion between the two fidget spinners. Now, what about the dispersion? See, the dispersion is independent of the gate distance once the gate distance is 1 Moret lattice spacing away. So, so that we can also understand, because if R is non-zero, so we're describing hopping, then at least one of these terms has to have the two exponentially localized Wannier states centered on different sites. That means, as I showed you before, that it cannot contain monopole contribution. It has to start with at least a dipole. And indeed, for the nearest neighbor ones, I show you what the momentum Fourier transform of a dipole looks like. You see it vanishes, as it has to, at small wave vectors. And so that means that it does not, it suppresses the contribution from small q, which means it's no longer sensitive to Xi larger than the Moret period. Okay, and so that explains why the shape of the dispersion is actually not changing. So what this would predict is that the effective mass of our excitations are not sensitive to how far the gates are placed, but the gap is. And this comes directly from understanding the binarization. So here are the actual hopping constants for a particular gate distance, which we chose to be 5 Moret periods. The term in the center is the on-site term. The values on the left, so you should think of them as the center is you hop from the center back to the center, and then this term is you hop from the center to this site. You see it's symmetric, and you see these hopping amplitudes are going down as you move further away. So indeed, it is exponential localized. It's a triangle lattice problem with a negative hopping, which explains why the minimum is at gamma. And you notice that the hopping constants are almost the same for the exchange and for the Hartree contribution, which explains why there's this, which explains why the shapes are basically the same. Okay, so now, what does this look like, therefore, for our excitations? So if we are at a charge neutrality point, then this Hartree contribution doesn't do anything. All we've got is the exchange. And then we get this, both for particle and for the Hall, we have a minimum at the gamma point with a dispersion that just looks like a triangle lattice hopping with an negative nearest neighbor hopping constant, plus a little bit more, but this is the basic term. Again, the y-axis is in units of the Coulomb scale. Now, if you go to nu equal to 1, because of this interference between these two terms, if we try to add a Hall to nu equal to 1, its dispersion is extremely flat. On the other hand, if we try to add a particle, as I mentioned, the dispersion doubles in width. If we go to nu equal to 2, because we add, subtract 2 of these Hartree contributions, the dispersion inverts. And so if you try to add a Hall, you see it's going to go still into these flat parts with a large density of states. On the other hand, if you try to add a particle, it still goes to this minimum. And nu equal to 3, you just invert more. Okay. And so you see that at positive integer filling, adding a Hall leads to heavy fermions because the mass here is large. On the other hand, if we try to add a particle at positive integer fillings, they go into this highly dispersive minima, and these are our light fermions. So the Sawtooth cascade transitions can actually be understood by trying to interpolate between these limits. You saw in the inverse compressibility data that Pablo showed that if you are at nu equal to 1 and you try to add a particle, you go into an almost incompressible state. Okay, well, you can think of this as having a nice, nice dispersion. You have a light fermions, and these light fermions, as I will argue, will form a Fermi liquid. On the other hand, if you try to take particles away, so you add Halls at nu equal to 1, the dispersion is rather flat. The compressibility is going to be high, and you're going to get this Sawtooth asymmetry between these two cases. So this is shown here, where we numerically just try to interpolate between the integer fillings by taking slightly determinant wave functions. So we allow for population of these 4 bands in different ratios, and you see, starting from nu equal to 1, going to nu equal to, starting from nu equal to 0, going to nu equal to 1, we start first by filling democratically these 4 pockets at the gamma point. So you have a Fermi liquid here, and at some critical value of nu, there is a phase transition in which one of these bands separates and eventually fills up while the other ones stay empty. Okay. Then you reach nu equal to 1. That's the exact dispersion I showed you. So the way this is being interpolated is that each integer is basically exact. This calculation was actually done away from the chiral limit to be a little bit more realistic. And again, we start at nu equal to 1. We add particles. They first go democratically into these minima while keeping the already occupied flat band here. And again, one of the bands will separate out. Eventually, you reach nu equal to 2, and you occupy 2 of these bands. And again, you get to the dispersion of the type that I mentioned. So the reason why the red and the green curves here are split as opposed to being on top of each other as in the chiral limit is because we broke one of the symmetries that is present only in the chiral limit. But other than that, you see that the shape of this dispersion is still basically the same. The minimum is at gamma, and then they're flat in this M to K prime region. And then you just simply continue this way until you fill up the band. So if you then ask for the total energy of the system, take a derivative with respect to particle number, you get the chemical potential. You see this cascade of the chemical potential with clear features of negative compressibility. Okay, you can do this by enforcing C2T symmetry. So you can say, you know, this is strong coupling, everything is gapped. Could you also get gapless phases? And I was hoping to discuss that if I still have some time. In any case, this calculation shows you that you get basically the same feature in the compressibility, even if you enforce C2T, which in this particular calculation at odd integer filling cannot open up a gap. So it doesn't really matter whether you have gapped or gapless phases for these cascades to be present. Needless to say, Pablo's already mentioned this. These cascades have been observed in Shahal Ilani's group, which plots. So this is the inverse compressibility. You see the Sawtooth asymmetry around each integer. And you also see this convex shape of the integrated chemical potential. So this is the chemical potential versus the filling. Here, this is sort of almost incompressible, and then it gets flat here. In other words, it is highly compressible, sometimes even with a negative compressibility, as you see in detail here. So in my opinion, this can be explained using strong coupling, as I discussed. There is additional data from Amir Jacobi and Pablo Jarillo Herrero's collaboration on samples which are probably hexagonal boron nitride aligned. There you can also see these sawtooth features clearly with negative compressibility. And I think in this case, at positive integer fillings, they even saw gaps. Okay, I don't think I have enough time to explain why negative compressibility is actually does not signify thermodynamic instability. For those of you who are interested in this, there's a very nice paper from 90s by Eisenstein, Pfeiffer, and West, where they actually measured this in a 2DAG. The upshot of the story is that you're actually not really measuring the thermodynamic compressibility of the system. You're taking away the Q equal to 0 part of it in this experimental setup. So there's no problem with compressibility, quote unquote, compressibility being negative. I don't think I have enough time to discuss that. Cascades of these transitions in twisted bilayer graphene were also observed in STM by Ali Yazdani, again, consistent with what I just showed you. The other thing that this picture explains is why the Landau fans point away from the charge neutrality point. Because it is only away from the charge neutrality point that you have light fermions. And so they're going to have a nice Landau orbits with well-separated energies, while if you try to go towards the charge neutrality point, they're too heavy. So you won't necessarily see the quantum oscillations there. All right, so now I want to, so how much time do I have right now?
Well, I think if you can use another 5 minutes. If
5 minutes. Okay, so this is going to be lightning fast, but let me just remind you what we did last lecture. We constructed these hybrid Wannier states. I think Titus mentioned them today. The particular direction along which we compute the projected position operator is shown here. This is the technology for this. I mentioned to you the wave functions have a rather interesting structure. They're not just simply Gaussians with peaks at the centers of the Wilson loop eigenvalues. These are really expectation values. You should think of them as a mean of a distribution, while the distribution has more structure. And so now what we wanted to do is we wanted to understand, first of all, kinetic energy in this basis by constructing a smooth gauge. This was done in this paper explicitly. So for those of you who want to know how to construct smooth gauge in the hybrid Wannier basis, please look at this paper. You see that the kinetic energy has 2 Dirac cones, and if you track the winding, you notice that the winding is the same. Now, what we did is we then ran a DMRG calculation with I-tensor in that hybrid Wannier basis on a spinless one valley model. Okay, we could not add spin and valley just simply because of the numerical resources. Now, but this was the first DMRG calculation on this problem. And what we found out is that as we change W0 over W1, so we start in a chiral limit, and then we crank it up to close to 1. Not surprisingly, at W0 over W1 equal to 0, we found a churn state, so quantum anomalous Hall state with C2T symmetry broken. That's very easy to describe in this space. It's just a product state because we occupy only one of the branches of this Wilson loop. Then, remarkably, there's a phase transition roughly at around 0.8, where the system recovers C2T. And it either breaks rotational symmetry or so it certainly breaks rotational symmetry, but whether it also breaks translational symmetry or not, we were not able to resolve within our numerics with the MRG. All right, so, but what we noticed is that the occupancy of various hybrid Wannier orbitals is almost always 1, with very little probability of double occupancy or single occupancy. Moreover, we found out that the equal time correlation functions between either the same churn number or opposite churn number is extremely fast decaying function. So it's basically only on-site correlate. This made us use this trial state for doing additional refinement, going to larger system size of this variational calculation. Now, I don't have enough time to describe the result of this variational calculation, just to show you that it recovers the result of the DMRG, and it also recovers this transition. Now, the upshot of the story is that there are 3 competitive states that we find in this calculation. So first is a quantum anomalous Hall state, which I already mentioned before, which is a gap state with a dispersion of the similar type that I showed you before, with a minimum at the gamma point. Needless to say, such states have been observed experimentally in samples which were hexagonal boron nitride aligned, and more recently even samples that are not, and even at zero magnetic field, but by Dima-Efetov's group. But there are 2 other states which seem highly competitive. Now, one of these states is a nematic state, so state which breaks rotational symmetry, but does not break translational symmetry. And remarkably, it also does not break C2T symmetry. Now, I showed you it was the C2T that gave you the same winding number of the 2 Dirac cones. And so what's basically happening is that you're moving these 2 Dirac cones closer and closer together. And now the minimum of the dispersion is still at the gamma point. Okay, even though the non-interacting problem would have a minimum of the dispersion at K and K prime. And that state is gapless. On the other hand, there was another state, which is also extremely competitive, which we found, which breaks translational symmetry and doubled the period. But it did not break C2T symmetry. Okay, we call that one a C2T stripe state. Remarkably, despite the fact that it did not break C2T symmetry, that state is gapped. So the question is, how is this possible? You have 2 Dirac cones which have equal winding number. You did not change their chirality. All you did is broke translational symmetry. How can you get rid of them? And the way to understand this is by this very nice picture introduced by Tomasz Duszek and collaborators, where you can think of it schematically as follows. Once we double the period, we need to fold our Brillouin zone. When we fold our Brillouin zone, then in addition to the 2 equal winding number Dirac cones that we had between the bands 2 and 3, we're also going to pick up new Dirac cones, which are for the bands away from the chemical potential. And these are marked by red and blue here. Now, it turns out that the topological charge of these Dirac cones actually now depends on the path you take between them, because of the presence of the Dirac nodes in the proximate bands sketched here. So, for example, you can't annihilate these nodes if you take them along this dashed curve, but if you take them along this solid curve, you can, because one way to think about it is that if you wind once around one of the nodes, the topological charge will change, and now you can annihilate. In any case, if you want to see the details of this, you can also see it in this paper written over here. So this is the actual mechanism. It's actually non-abelian Dirac node braiding that allows you to have a state which does not break C2T, it only breaks translation symmetry, does not break value U1 symmetry, does not mixing the remote bands, and still gaps out the spectrum. So we show exactly how this is done. Here, there is follow-up DMRG work by Mike Zalato's group with more accurate algorithm, which basically reproduces our results. They also find the transition at 0.8. They find quantum anomalous Hall state, and there the MRG is able to resolve this competition in favor of this nematic state. But again, they find that the energy of the stripe state is extremely competitive. Since we don't really know the Hamiltonian to that degree of detail, these are states which we should consider. Now, finally, I'd like to say that there was a recent experimental report by Amir Jacobi and Pablo Carrillo Herrero's collaboration, where they saw signatures of states which have this doubling of the unit cell, broken transition symmetry. Okay, so since I'm out of time, let me just stop here and take questions.
All right, thank you, Oskar. So I think we have time for one or two short questions.